All right, this is a re-record of today's lecture, so I will do my best to recapture everything that we talked about in class today, and probably be throwing a little extra because I don't have to ask whether the class has a question or not. So as a result, I can probably cover even more material. So let me crank up the recording a little bit here because I'm speaking a little bit softer in my office right here. Okay, there we go. All right, so we are going to translate this code into TTP ASM, and I'm going to crank up the recording level just one more notch because I want to be in the yellow region. There we go. Even when I'm speaking softly. There we go. All right. Um, all right, so we are going to get started, and you can see that I'm using a new file. It is llist1.ttp ASM instead of 0. So there we go. We have the usual entry code, no op, LDI D0 to initialize the stack pointer, LDI A.6 plus to specify the return address, decrement D, STDA, so this way we push the return address on the stack, JMPI to main, this is how we continue execution in main, treating main basically as a regular function, and then a halt instruction because when we're done with main, there's nothing else to do. And then after that, we try to define the structure. So in this case, x underscore v is the offset in number of bytes from the beginning of a structure to find member v. So it is 0 because the first member of a structure is at the same address as the beginning of the entire structure itself. X underscore next is x underscore v1 plus, and this is because v as a member is only 1 byte long. X underscore size, which is the size of a struct X. That is the offset to find the last member of the structure, plus the size of the last member, which is next in this case. Because we are using TTP, so that means all the addresses are only 1 byte wide, and that's why we have a 1 plus. All right, so after that, we define the global variables. So N3 is defined as byte 2 and then byte 1, byte 0. So basically each byte, okay, BYTE, is not exactly an instruction. It's more, we call these, directives. So what they do is they reserve a byte, just like, the instructions, like JMPI reserve, 2 bytes, except, instead of an opcode to go into those locations, we can specify exactly what to go into those locations. So N3 is a label, but the label contains the address of the byte 2 on line 14 in the assembly code. So that means, N3 used as a label is the address of N3, and N2, does have the second member or next as a member pointing to N3. And then M1 has the value V being 16 in decimal, and also, it points to N2. So that's how we initialize, or that's how we specify global initialized structures. And then we have main over here. Main has got a few things. It has got a local variable pointer, PTR, and this is the first local variable in terms of the declaration order. So it is the lowest in the frame for main. And then we have main array, which is the next item. It is main PTR 1 plus, and that's because PTR itself is just an address. It only takes 1 byte on the stack. And then we have main underscore I, which is local variable I. This one is main array 3 plus because array itself takes up 3 bytes, and that's why we have to add 3 to the offset to find array as a local variable. Now we have a main LVS, local variable size, which is the offset to the last local variable plus the size of the last local variable. So with all of this calculated, I can now finish up the allocation for the frame. In other words, what we are doing here is we are allocating all the extra bytes on the stack for the local variables. And by subtracting main LVS from the stack pointer, we are allocating. And then to deallocate at the end of the function, we add the same amount to the stack pointer. At which point the stack pointer should be pointing to the return address again, which means we can now execute the usual code to return to the caller. So we pop the return address and then do a JMPV back to the main, excuse me, back to the entry code. All right, so right now we can implement line 16 of the C code, which is taking using the address of N1 to initialize PTR. So N1 is just N1. So LDIA N1 is getting the address of N1 into register A. So we can now say register A is the address of N1. And then what we do is we compute the address of PTR or the pointer as a local variable of main. So that would be LDIB main pointer, add BD to get to the address of pointer, and then do a STBA. So that will store the address of global variable N1 into local variable pointer PTR. And then we LDIA with 0. That's the right hand side of the next statement in C, which is line 19. And then we do LDIB main I, add BD, STBA. So that would initialize local variable I to 0. And now we have the while loop. And this is while begin at the beginning of the loop. And then we have while 0 end to mark the so this is the label to mark the byte after the loop is completed. And at the very end of the loop, we need an unconditional branch back to the beginning, because otherwise, this would not be a loop. And now we have an infinite loop, but that means, we just have to figure out, what reason do we have to exit the loop. And the reason to exit the loop is when PTR is null. So that means we have to find the value of PTR first. So we have LDI ABC, would be fine here. So I'm going to use LDI A main PTR. That's my offset. Add AD, that's my address. And then we have LDAA. So now we have the actual value of pointer. And then we can now do an AND AA to make the value of PTR to go through the ALU, therefore changing or updating the the Z for 0, the 0 flag. And if it is 0, then we can get out of here. So we go to while 0 end in this case. So now this part here is when PTR is not null. So if PTR is not null, then we need to go to line 22 in the C code, which means we have to get to the value of member V of the structure that PTR is pointing to. But PTR is already in register A, so we can just utilize that. So we have LDI B with X underscore V. So that's the offset from the beginning of the structure to member V. And we just need to add this to the address of the structure itself, which is already in register A. So we say add AB. And now A is the address of member V of the structure that is pointed to by PTR. Okay, so I'm going to comment here. A is the address of the member V of the structure that is pointed to by PTR. All right. But that's just the address. So we need a LDAA because we need the actual value. So now A is actually the value of member V of the structure that is pointed to by PTR. So that's the right-hand side of the statement on line 22. Now we move on to the left-hand side of line 22. So this one is indexing. We are looking at element I of the array, named array. So which one you calculate first is not really that important because we need both in order to finish the calculation. So I'm going to start with I, which is the index. So LDI main I. Forgot about which variable I want to put it into. So I have to put it into anything other than register A. So B or C will work in this case. So main I. And then we add BD so that we have the address of I. And then we do LDBB so that we actually have the value of I. So I can say B is the value of local variable I. And then I need to find out where the address of the entire array is located, because this is how we do indexing. So that means I need to do a LDIC. So we are close to running out of registers in this case, but not quite. Okay, so we can LDIC with main array, and then we add CD. So this way we have the address of the entire array, which is all we need. We don't need to dereference one more time, because I need to do the indexing. So now I can do add BC or add CB. It doesn't really matter which way I go. So we'll just do add BC. So that means B is now the address of um, array bracket I, and that's exactly the location where we need to do the store. So we do a store here to locate to the location pointed to by register B, and then the value is already in register A, and that will complete line 22. And then we need to increment I, which means the address of I is not kept around, because we need all three registers in that case. So we just have to do it again. So load LDIA with main I, add AD, so we have the address of I. But right here, we have to make sure that we use a different register to store the value of I, because that is going to be incremented. But then we also have to store it back to I. So that's why, I'm keeping A as the address of I and B as the value of I. This is the updated or incremented value of I, and it's stored back into the address of I, okay, of the location of I. And then after that, we have line 24. So we have the LDI main PTR. This is the offset to local variable PTR. Add AD. This is the address of PTR. And then we have LDAA. This is PTR itself, which is the address of a structure. And then we have an LDIB with the offset to member next. And that's the purpose of the label x underscore next. And then we add A and B together. Which one is added to which one? I think there is a. Oh, right. Okay, so in class, I did a little bit of optimization here. So I put the value of PTR into register C, because I need the address of PTR itself for something else later. So now we add BC or CB, either way is fine. So now C is the address of the next member of the structure pointed to by PTR, but we need the actual value of the member, not just the address. So we need a LDCC here. So now C is PTR points to next. And then we have the store, right? This is not by the time we get to line 73, we are done with the right-hand side on line 24 of the C code. And now we need to store to the left-hand side. The left-hand side is PTR. We still have the address of PTR stored in register A at this point. So that means that I can just do a store to register A, or where A points to, and then C is representing the value of the right-hand side. So that's what we need to do. And I believe this code is done. Okay, so this time I did not test the program incrementally. So let's see whether this works or not. Now we go to here, submit list list1 .ttp asm, and we'll give it a try, see if it works. So this time, I used the registers a little bit differently compared to last time, and we'll see. All right, so this is the run time behavior. Um, the analysis of how the locations are being used is still the same. This location was used by the entry code, which has no name, to call main. And so when main is done, this is the return address back to the halt instruction. And then these 5 bytes are used by main as its frame. So if you want to color code this, this is color code like that. So this is the frame. Oh, actually, I take it back. It has to include this one too. So all of these collectively is the frame of main because it consists of all the local variables, the return address, and optionally parameters. But main has no parameters, and that's why there's nothing here. And these are the values, that we think should be there by the time we are done with the code, because PTR has to be null because that's the only reason why we are exiting the while loop. And then the values of the V member of the structures N1, N2, and N3 should be in array bracket 0, array bracket 1, and array bracket 2, respectively. And then I needs to be 3 because it is incremented 3 times. So it was initialized to 0, but after incrementing 3 times, it should become 3. So that's why we should expect these particular values to be at locations FA all the way to FE. The return address, I believe, is just a 9. So, we'll just put 9 here. All right, so this is what we're expecting. And now we can go to the analysis tab and just to see whether that is what's happening or not. FA gets 0, 0. So we can double check that. FA gets 0, 0. Okay, checked. And I'm just going to be a little bit lazy here. I will just kind of take a snapshot of this and put it into this graphics viewer here, and then put it always on top. So this way I can kind of just go to one spot and double check all of those values. All right, so this is it. And we also want to make sure that the stack pointer is back to 0, 0, and we are halting at the only halt instruction here. So that part is working fine. So now we just focus on the changes to memory locations, and particularly the last changes to each location. FE is getting 3, and we can see the FE is the address of local variable I. It is supposed to get a value of 3, so that's good. And then we move back up. This is FD getting a 2. That is the last element of the array, and it is supposed to get a value of 2, so that's good. And then we get to here. FA is supposed to get a value of 0A. That's our pointer. But that's not the last update. The last update, changed it to a 0. So this is, because we're moving back in time. So this one is actually not that important. This is also not important because that's the previous value of I. Now this one is important because FC, we have never talked about what value it should get. It should get a value of 5. Yes, so that is as expected. And then we go back and this is another update of the pointer. Okay, it is F0C in this case, but that's also when we are looking at this backwards, it is not important because we know that it ended up with a 0 at the very end. And then we go back up. This is the value of I getting incremented to 1, but we know that the code exited with the value of I being 3, which is correct. And then finally, we have FB getting a value of 1, 0, which is 16. So that's also what we're expecting. So the program does work 100% this time as well. The code is a little bit different from what when we talked about it the first time. All right, so that pretty much concludes a recap of today's lecture. It is super fast this time around because I did not do the incremental debugging. But the incremental debugging can be described, just kind of like work a few lines, put a halt instruction, you run it through and make sure that all the locations that you expect to be changed is changed accordingly. All right, so this gives us a little bit more time to talk about the new program that you need to write. So I can actually talk about it a little bit here. All right, so we are done with list, okay, and I can send this one to you guys too if you want to, but I don't think it's much different compared to the one that you got from the announcement, so I don't think that really is necessary. So instead of doing that, we are going to look at Traverse and the provided code for Traverse in TTP ASM. All right. So we got a typical entry code here to call main and then return, when main is done, it returns to the hold instruction. And then we got this thing here. So I'm going to talk about, how to work on this in an incremental fashion. Okay, so that's, what we're going to do now. So what I'll do instead is I am going to create additional versions of Traverse and to basically signify, what you can potentially do to implement this program in an incremental fashion. So traverse.c, and I'm going to make a copy of that. So I'm going to copy traverse.c to traverse.0.c. Okay, so this is the first version. And in the first version of Traverse, okay, now the main program is already done. This is entirely done for you. Okay, so you can go to the Traverse itself, and the first time you try to implement this program, you might want to make sure that you can get to pointer. In other words, you just say, okay, I want to get to pointer, okay, and nothing else, okay? Because if you cannot get to pointer, the value of pointer, then there's really not much you can do about it, okay? So what that means is, when you're in the debugger, you want to be able to make sure that you can get to the address of whatever you used, whatever the main program used, as the address of, N1, N2, all the way up to N5. So you want to make sure that this pointer is in fact the address of M1, if you are implementing the code as it is here. So once you can get to pointer, then you can try to make this program a little bit more complicated. So I would do it like this. Okay, so if pointer, just give it a conditional statement here, put a halt instruction here, and put another halt instruction here. So that means, this implementation of traverse is not going to return. It will end up with either this halt instruction or this halt instruction here. But depending on which halt instruction it ends up at least you know whether the condition of if pointer is working or not. But in order to check that, you also want to kind of check it with different calls of traverse. So you want to basically call traverse with a null pointer instead of the address of one of the nodes. So this, if you call traverse this way from main, which means you also need to make some matching changes to main, you can pass a null pointer instead of the address of M1, in which case, you should end with this halt instruction. On the other hand, if you kept the original code like this, then you should end up with this halt instruction here because pointer is not null in that case. So if this code works, okay, and you need to give it two different test cases to make sure that this code does work, because you need to make sure that when pointer is null, it ends up here, and when pointer is not null, it ends up here. So if this code works, then you can move on, right? So this is the first version. So I'm gonna save this. And now I'm going to give you the second version of what you can potentially do. Okay, so we'll look at one. Okay, I'm copying the original to traverse1.c, and then we look at traverse1.c. Okay, so the first version is basically saying, okay, let's forget about the recursive call. Get rid of the recursive call. Okay, and just say, okay, whatever this portion is specifying, I just want to make sure that is the case. No. How do you test this? So if this is the program that you're testing with, then what you have, okay, when everything is all done, then you should be able to find, buffer bracket 0 to have the value of member value of n1, which is a 5. But you should also find that the pointer p in main should be pointing to the second element of buffer, which means the p should be the address of array bracket 1. Now, how do we know this? Because this particular statement is going to the value of the structure that is pointed to by pointer, but since we are passing n1, the address of M1 as pointer PTR. So that means the value member is a 5. So the right hand side of this assignment is a 5. But where we are copying that to is the location. that is pointed to by a pointer, which in return is pointed to by p-array. P-array as a parameter is the address of P. So that means the first dereference will get you to P, and then the second dereference will get you to what P points to, which is the first element inside the array buffer. So that's why, the first statement on line 14 would update buffer bracket 0 of main to a 5. The second statement, which is line 15, is incrementing whatever P array is pointing to. So once again, P array itself is the address of P. So after you dereference it once, it becomes just P, and that is what we're incrementing. So when you increment P as a pointer, which was originally pointing to the first element of buffer, then it should point to the second element of buffer after this is all done. Now this you can actually verify using GDB. So you basically compile this program, traverse1, traverse1.c in GCC, and then you GDB it, okay? And then we just have to look at main, okay? So you can debug this program in a different way, but I'm just going to debug it in C, and we put a breakpoint on line 32, and then we run this code. So now I can double check. I can say, okay, and you can actually use these expressions because these expressions are actually, they can be parsed in GDB. It is true. Okay, so that's good. And then we also want to make sure that P as a pointer in main is the address of array bracket 1. And, oh, it doesn't like that. Oh, it's buffer. Okay, never mind. Okay, that's my bad. I thought it was called array. It's actually buffer. But the equality does hold in this case. Okay, so that's that. So I'm just going to modify traverse1.c because I don't like my comments to be inconsistent. So we'll just change this one back to buffer1. So that's how you check the code and make sure that you can get these two statements done without having to worry whatsoever that there's a recursive portion, right? So the recursive portion is really kind of the last thing that you need to do. So let's go ahead and make another copy of traverse. So we are copying traverse.c, this time to traverse2.c. So if you are to use traverse2.c, then we are, because we're assuming that line 14 and line 15 are both done correctly, and the control structure, the conditional statement is also done correctly. So we can basically just take out one of the recursive call. Let's say we take out line 16 and we just focus on line 13. So that means we are only traversing, or we are only following the L pointer. So that basically degenerates the entire thing into um, a linked list, like a linear linked list. So L is the first pointer. So that means, N1 will, N1 is followed by N2, and then N2 is done. Okay, N2 is, um, it does not have a L pointer anymore. So in this case, okay, in this particular program, what I'm expecting this to happen inside main is P would get two, there will be two values stored into buffer. So buffer 0 is, but because we are calling traverse first, so that means the inner, that means the deepest recursive point is going to store first. So that means this is going to store the value member of n2, so that would be a 3, and then buffer 1, which is the second element of buffer, is actually going to store the 5 in this case. Because we store two things, so that means the p as a pointer in main would be the address of the third element, because basically it is always pointing to the next available element of buffer to store something. So after this is all done, I'm expecting line 34 to line 36 as conditions to be true. Okay, so we'll save this, and then we're gonna test this. Okay, so this is traverse 2. So we have a gcc-g-o traverse 2, traverse2.c, gdb traverse 2. and then we list main, put a breakpoint at the very end of main, which is line 32, run the code, and now we check the conditions. Is the first element of buffer having a value of 3? Yes. Is the second element of buffer having a value of 5? Yes. And then we check what about P? Does P point to the address of the third element of buffer? And it is also true. So that means all of these conditions should be also true when you look at the TTP ASM implementation. It's just that in that case in the TTP ASM implementation, where do we find all of these things? So that's what we'll talk about a little bit here, just so that it makes it a little bit easier for you to debug the program. And to do that, okay, we need to look at the original traverse.ttp-asm because all the stack operations are specified here. As we can see here, we push the return address back to the entry code first. So that's a 9, and it would be at a location of FF. So if I were to go back here, okay, I'm just gonna make a copy of this, copy duplicate. There we go. So the duplicate here is going to be for traverse. So this part is still the same. But these are going to be a little bit different. So I'm going to get rid of these and also get rid of these. So now we switch back to the code, and then we ask how many bytes do we need for the local variables of main. So local variables of main, there are only two. Buffer is 5 bytes long, and then P is only 1 byte long, so there are 6 bytes altogether. So that means when we go back to this picture, we basically say, okay, these 6 bytes, would be from F9 all the way to FE. Those would be the local variables of main. And this particular one is buffer bracket 0, buffer bracket 1, buffer bracket 2, buffer bracket 3, buffer bracket 4, because all of these are local variables. I mean, okay, I take it back. Buffer is one single global variable, but since it is an array, it has 5 elements here. And then this is the last one, which is PTR. All right, so when we test the program, so let me change the color code too, because that makes it a little bit more consistent. So now the colored portion, this portion here, becomes the frame of main. And so basically, when we specify the earlier result, okay, so let's go back to the expected result here in traverse 2. So I'm only using this as an example. Obviously, you can extend this to the other test cases. So in this case, we're expecting buffer bracket 0 to be a 3. So that means we're expecting this to be a 3, this to be a 5. These locations are uninitialized, which normally means they are zeros, okay? And then PTR is going to be the address of buffer bracket 2. So that means this should be FB over here. Let me double check. Yep. Okay. So that means this one should be as hexadecimal FB, and that's what you should see after you run the TTP ASM equivalence of Traverse 2. So if that is working, well, that's actually really encouraging that, right? Because if this is working, then I think you're ready to tackle the original Traverse, which means you only have excuse me, one more recursive call here. And this is the last recursive call. If you can get line 13 done, line 16 is pretty much the same thing, except, it is looking at member R. The, yeah, so in terms of the output, when you include the last, traverse, then for this particular program, what you should see when everything is done is that buffer bracket 0 should be a 3, buffer bracket 1. Okay, this is double equal because I'm not changing those locations. I'm specifying what should be at those locations. This should be a 4. And then buffer bracket 2 should be a 5. And then buffer bracket 3 should be a 9. Buffer bracket 4 should be a 10. And then P should equal to buffer bracket 5, which doesn't exist, but we can still calculate the address and compare that to the current value of P. So that is still possible. And just to make it easier for you guys to test whether your code is, let me see, how should I put it? Okay, I'm just undo it. Okay, so all of these conditions should be true when we get to the last line of main, given this is the program. So this is one way for you to test your code as well. It's just that in the previous one, so basically traverse is traverse3.c because that's the original. Just for your convenience, I'm gonna just make a traverse3 here. All right. So I'm now giving you some stages of how to write your code and how to debug your code. Hopefully this is going to be helpful to you to kind of write your code. So I'm going to zip up all of this stuff here. So look at traverse has 0.c, traverse 1.c, traverse 2.c, traverse 3.c. So that basically gives you 4 stages altogether to implement traverse, and each stage should be broken up into multiple steps just so that you don't write too much code before testing. And then obviously I will also include traverse.ttp asm into the new zip file. So now you have these stages. Oh, this is not really necessary, but I'm going to include traverse without the 0, 1, 2, 3. And I am going to send that to you right away. So now you have the various stages to consider when you're implementing the code. So I would another update. Okay, so another update for traverse. See attached. And now you know that there are stages that you can work on when you're trying to implement the Traverse program. So traverse.zip is what I need. Okay, publish. There we go. All right, and I don't need this anymore. But I cannot overemphasize, the importance of, how, just knowing what should be in memory. Now, this one is only seen from the perspective of the main function, in terms of the frame. You probably want to work out, in the first call to traverse, what should be on the stack. So I can spell that out a little bit for you. This would be p array as a parameter. This would be ptr. Um, is it called ptr? I cannot remember. Oh, yes, it is PTR. This one is actually called P, not PTR. So this is parameter PTR of traverse. This is your P array of PTR. And this is the return address to go back to the previous one. So these 3 bytes together is the frame of the first invocation of traverse. And depending on what you're testing and what you use, to pass as these 2 parameters, they can be different, okay? But assuming that you are using the original code, so that means your PTR should be the address of N1, and the P array would be FE, because that is the address of local variable P of main, and that's why P array should always be FE, regardless of which frame of traverse we are looking at. Uh, now, what is at FE would actually change over time. So this will start with F9 and then FA and then FB and so on. So that part does change over time. But when you look at the parameter P array, when you call traverse, it should always be just in hexadecimal FE. Now, PTR does change over time. It will go from N1, the address of N1, to the address of N2, and then eventually it will be 0, at which point, the recursion stops and then it just simply returns in that case. The deepest recursion is going to be 3 levels deep, okay? So you can potentially have another frame over here and another frame over here, but that should be the deepest level. No, I take it back. The 4th level is actually here, because the last level is when you have PTR being a 0. So that means you can potentially use locations all the way down to here. So I'll just kind of color code the frames. So this is another potential frame. Okay, we'll use this color. And this is the third frame. Okay, we'll go for green here. And this is going to be the last frame. You can be 4 levels deep. Now I can show you, how it can be 4 levels deep in the C code. So give me a second here when I color code everything here. We'll just go for this color. There we go. We have used it already. Let's pick something else. I think orange will work fine. There we go. Okay. So the reason why I know it can go 4 levels deep is like this. Okay, so we can now go back to the original traverse code. So gcc-gso traverse gdb traverse dot just traverse. There we go. So when you set up a breakpoint, you can set up a breakpoint in at the beginning or the entry point of a function. In this case, the function is, well, traverse. So now we have a breakpoint at the entry point of traverse as a function. And then when you run the code, this is the first level, this is the second level, and this is the third level. But that's okay. Okay, you say that you might say that, but Tech, I thought we were going to go for 4 levels. Just wait. Okay, this is again the third level, and now this is the fourth level. So how do I know this is a fourth level? We can use backtrace, BT. So when you look at BT or backtrace, um, with traverse, this is frame 0. It is called by traverse, which is called by traverse, which is called by traverse, which is then called by main. So that means we now have 4 invocations of traverse on the stack. And in that particular case, by the time we get to the null pointer, in traverse, we would have the first invocation, with n1 or the address of n1 as pointer, and then the second invocation with n2 as the address of n2 as the parameter pointer, and then the third invocation would have the address of n4 as the value of the parameter pointer, and then the last level would have 0 as the parameter pointer. But you can also see that in every single case, p array does not change. It is always exactly the same because that is the address of local variable p in main, and that address does not change. Now, what p points to in main does change over time, but not the address of p itself. All right, so I think that is all that I need to say. I'm looking at the time. It's only 42 minutes, but I have everything already said. Okay, so I'm gonna stop the recording and upload it.